Okay, so let's look at electrochemical reactions. So here we have a situation. Under standard condition, one of these reactions will occur and the other will not. So we have two equations. We have copper existing as a solid reacting with iron sulfate, aqueous, to produce copper sulfate, aqueous, and iron solid. So just a quick reminder, these things we have in bracket here, they represent the state. We have copper in the solid state, iron sulfate in the aqueous state. To produce, the arrow means to produce, to give, to form copper sulfate, aqueous, and iron solid. Okay, we have another equation, copper sulfate aqueous reacting with iron solid to produce copper solid and iron sulfate aqueous. So it's two different reactions. If you step back and look at the reactions, you could see we have some form of displacement where the copper is displacing the iron and we end up with copper sulfate and the iron is displaced. Here we have the copper is being displaced by the iron displaces the copper, and we have iron sulfate and copper being given off. So under standard condition, only one of these reactions will occur. So today we're going to try to find out which one will occur. In order to do this, how can we tell which reaction will occur under standard condition? We need to be able to do basically four different things. Identify atoms and ions, identify the atoms, identify the ions in the compounds, identify oxidation state, interpret activity series table, and write half equations in terms of oxidation and reduction. So I have here we have a activity series table here. We're going to look at it soon. So first, we're going to be able to identify the atoms and the ion in compounds. So let's examine the first equation. So the first equation we had copper displacing the iron in the iron sulfate to produce copper sulfate and iron. So here we have just the copper by itself. It has an element existing by itself as an oxidation state of 0, or an element bonded to its own self also has an oxidation state of 0. So here we have iron and sulfate. These are sulfate by itself is a polyatomic ion, and it can be represented as SO4 2-. Since there's no charge over here, we know the iron itself had a +2. Since there's no charge, net charge, which means the charges must have added up to equal to 0. So if this is -2, this had to be +2. So here we have copper with a 0 oxidation state, iron with a 2+, sulfate 2 SO4 2-. So here we're going to look at this set here. Again, sulfate is SO4 with a 2-. We right away should be able to tell that the copper would also have a 2+. For the same principle, there is no net charge here, and since there's no net charge or charge equal to 0, we must have these numbers add up to 0. And also iron existing by itself has an oxidation number of 0. So let's look at what we're able to do. We can identify the atoms and ions in the compounds. So we identify the atoms and the ions. We identify the oxidation state. And next thing we need to be able to do is interpret activity series table. So let's take a look at this activity series table. So this table gives a list of different metals, and we have hydrogen somewhere along. Hydrogen is placed along with the metals. Those at the top portion are the most reactive ones, and those at the bottom are the least reactive. This tells us the ease of oxidation. Those that are further up are the ones that are going to be oxidized, and the ones that are further down are the ones that are going to be reduced. Once there's a difference, once we choose elements that have a difference, we could actually have a difference in potential. So let's locate our iron and our copper. So these are the two ions we have. Iron is found here, and copper is found here. So they are significantly far apart. So from this, we can tell that iron is one that is going to be oxidized, and copper is going to be one that is going to be reduced. When we're writing oxidation and reduction, for oxidation, okay, let's try this in black. Oxidation, by definition, is the loss of electrons. So if you're losing electrons, we normally start our oxidation, we're writing oxidation, we start with the metal by itself. So iron is going to be the one that's going to be oxidized. According to our chart, iron is further up. So iron to iron 2 plus 2 electron, where we're losing electrons. So this is how we normally present our oxidation state. So iron is being oxidized. I mean, it loses an electron. Also, oxidation involves the increase in oxidation number, moving from a 0 to a 2 plus. Is that the case happening here? No, it's not. We're actually moving from a 2 plus to a 0. So we right away could tell this is not going to be the equation that's taking place. Okay, let's look at reduction. For reduction, we would start with the iron. So we would have, if that's the case, based on our activity series, the copper would have been reduced. So we'd have copper 2 plus 2 electrons to give copper. And if we look up on our equation, that's not what we have in here. We actually have copper 0 going to 2 plus. So this equation is not likely to be the equation in question. So let's look at the second equation we have. We have copper sulfate reacting with iron to give copper and iron sulfate. So let's try this. Copper sulfate reacting with iron to produce copper plus iron sulfate. And if you were to separate our ions, let's go back to our red marker, we would have copper with a 2 plus for the same reason we had before, because we know sulfate has a 2 minus, and then we have an iron 0, and the element by itself has a 0 oxidation state. Copper here is also 0. This is iron with a 2 plus and sulfate with a 2 minus. So from this, we could see we are moving from copper 2 plus to a copper. This is exactly what we wanted. And we also move from an iron 0 to an iron 2 plus. Let's check this out. Iron 0 to an iron 2 plus. So this would be the equation that is the right equation. I hope this helps in being able to determine which equation, and you could now break down your equations. Thank you.